All right, keep working on this problem. I'll give you all about 2 to 3 more minutes before I go over the solution. And again, if you have any questions, please let me know. Alrighty, let's go ahead and go over the solution for this problem. And like I said, this one is a little harder. I am going to admit that. But let's observe the hint. Because right now, here's my thought process with this series. Nothing seems to be working. I can't think of a subject to compare with. I can't think of something with that. If you were here yesterday and you saw the very last example I did, I can't take the absolute value. That won't help me because I have 2 plus sine of k, not just sine of k by itself. So that's not going to help me at all. And so if I'm stuck there with any function that I know of an interval dou, I could try to use that to my advantage. And so here's what I mean by that. I know from way back in the day that sine is always in between -1 and +1. In my denominator of the series that I want to test, I have a 2 in there. So I can add 2 to everything in the inequality, and I have a bound for 2 plus sine of k. And that's 1 is less than 2 plus sine of k, less than or equal to 3. Which makes sense because since we have a function plus a constant, that tells us I shift vertically up or down by 2. So that tells us that we shifted vertically up by 2. So that's nice, but I don't necessarily have the 1 over 2 plus sine of k. But I could still use this to my advantage because since I now know that 2 plus sine of k is between 1 and 3, I'm no longer including 0. So this tells me that no matter what I find, 2 plus sine of k is not equal to 0. And why do I want to observe that? Because that means it is safe for me to divide everything by 2 plus sine of k and adjust accordingly. And so if I do that, here's what's going to happen. And I'll observe with the right side of that inequality. 2 plus sine of k less than or equal to 3. I'm going to divide both sides by 2 plus sine of k. Left-hand side cancels out to give me 1. So I have 1 is less than or equal to 3 over 2 plus sine of k. And then what I need to do is if I divide both sides by 3, I now have an inequality in regards to the terms of the series that I dealt with at the very beginning, which is 1/3 is less than or equal to 2 plus sine of k. And I say from yes, we can start making some headway into our conclusion. So I say because I have the terms in my series, let's actually write that, a of k is greater than or equal to something, even though 1/3 is a constant, I can still treat that as terms of a series. It'll just be a constant. So I claim that I'm going to use direct comparison test here because I now have a of k is greater than or equal to the constant 1/3. And not only that, for me to complete direct comparison, I need to do the following. Because I showed that the terms in the series that I want to know convergence on is greater than or equal to something, then for what I need to show in order for me to conclude by direct comparison test, is that I need to show that the series with the terms b of k diverges. So let's do that now. Terms of b of k equals sum going from k equals 1 to infinity of 1/3. And let's talk about strategies for series here. If I have a series that is a constant just throughout, it's going to automatically be a divergent series. And here's why. So that's going to be my claim. And the reason why a series with nothing but constant terms in it diverges is because of the divergence test. because the limit of the terms in the series is just 1/3. Limit of a constant is just itself. That's definitely not equal to 0. And so what that tells me is my original series is greater than a series that's blown up to infinity, which means that my original series also diverges. So thus, by direct comparison test, my series 1/2 plus sine of k diverges. And I will admit that this one is a little bit trickier because of that 2 plus sine. My strategy with that, if you do a counter that on the final, is first ask yourself, okay, what bound do I have for that function? In this case, I've used the fact that sine is always between -1 and 1. And I manipulated that to give me the denominator, or a bound for the denominator. And then I divided everything to give me a bound for the terms in the series that I want to test. I'll scroll back down in case y'all were writing. So y'all can copy that down. If y'all have any questions about that, please let me know. I'll take a sip of tea to give a minute pause. That's a good point. So what Matthew is asking is, can we just use divergence test from the start? And I actually say yes. And the reason why you can add that, we know that sine oscillates. It never levels out. And all I did with that denominator is that I shifted it vertically by 2, and then I took the reciprocal. So that's not necessarily going to affect my for that. Fair enough. Smarter one way to tackle these guys. Sure. So Matthew asked you to review, so let's review that real quick. So my end goal is I did the direct comparison test on this guy. I don't know. The caveat is I don't know what to compare with as of right now because of the 1/2 plus sine portion of it. So what we do is we now check based off of a bound for a function that we know how to review that. In this case, I saw that I have sine, so I'm going to bound that between -1 and 1 because we know that sine is between -1 and 1. My denominator is just my sine function shifted up by 2. So I can add 2 to both sides of that inequality. And I get 1 plus 2 plus sine of k is in between 1 of 3. What that inequality tells me is that 2 plus sine of k does not equal 0. And so that tells me I can divide by 2 plus sine of k to give me 1 is less than or equal to 3 over 2 plus sine of k. Meaning that I have 1 is less than or equal to 3 over that, and then move the 3 over. I now have a bound of 1/3 less than or equal to 1 over 2 plus sine of k. So now I can use direct comparison test because the terms of the series that I want to know convergence of is greater than the terms in a series that I know is divergent because my terms on the left-hand side are constant. And so the sum of just 1/3 will be divergent by the divergence test. And so therefore I can conclude by direct comparison test that the series diverges. Does that help out, Matthew? I don't know how quickly or how you wanted me to review that. So if you still have questions on that, Matthew, you can send that to me. All righty. No, you're welcome. All right. So with that, let's move on to another fun series to tackle. And so here we go. And so again, for the net series, check convergence or divergence of the following series. N squared plus 1 divided by 5 to the n. Give you all a few minutes to test that out. And if y'all have questions, let me know. I'll give y'all about another 2 to 3 more minutes before I go to the solution. If y'all have any questions on this problem, again, shoot me a question. I'll try to answer it as best as I can. Alrighty. Let's talk about the solution for this guy. First, I have to figure out what test I want to use. Let's see, divergence test is not going to work here because by growth rates, the terms are going to go to 0. So that tells me nothing. But here's kind of my thought with choosing the test for yet. So because I have that n squared and a 5 to the nth power, I have 2 tests that can help me quickly cancel out 5 to the n. And that's ratio test and root test. Ratio test because I'm taking a ratio, which means I'll do a lot of cancellation. Root test because since I'm taking the nth root, the nth power will come into play. And I'll take the nth root and then the nth of something to the nth power. So that's going to narrow it down to 2 tests that I could use. Because of that denominator 5 to the n power. Now, I'm going to have to choose which one I would prefer. Because in my numerator I have n plus 1, I'm actually going to choose one of them over the other. And that's ratio test. If it was just n squared, I would say you can use either root or ratio test. But because I have a plus 1 in the numerator, doing it with the root test will make it a whole lot harder.
Don't you need to have it to the nth power in the numerator too to be able to do root test?
So the reason why I say if I do have the n squared is because of this result. And so even if I did just n squared over 5, and that's a really good question.
Okay.
To the nth power, I could rewrite as n 1 over n squared over 5. And so when I take the limit,
It would then just be 1/5. Okay. That makes
Bingo.
sense.
Yep. And that's a
Cool.
really good point to make. But because of the +1, I can't quite do that little trick. So now, let's pick it up with the ratio test. My advice always for ratio test is go ahead and list out what your n+1 term is and also your a of n term. So that way you have it set up and ready to go for ratio test. So because I have my subscript n+1, what that means is everywhere that I saw an n, I'm going to replace with n+1. So that's going to become n+1 as inside squared plus 1 divided by 5 raised to the n+1 power. And then I'm just writing this down for reference, so I have it. Alrighty, so I have that down for a reference. Let's go ahead and try out ratio test. So I want to have L be the limit as n goes to infinity of the absolute value of n+1 over a of n. And this is more of my preference. You can keep this however you like. To me, it looks a lot nasty to write both a of n+1 and a of n in one fraction. So one thing that I like to do is I like to separate a of n+1 in the current term like that. So that way I can now think of it as I'm multiplying a of n+1 or the next term over times the reciprocal of the current term. And so with that, I now have the limit as n goes to infinity of n+1 squared plus 1 divided by 5 n+1 times the reciprocal of a of n, which is 5 to the nth power divided by n squared plus 1. Next thing I do, I check to see if I have some cancellation. I do mainly because I can rewrite 5n plus 1 as 5 times 5 to the n, which means I have a 5 raised to the nth power in the denominator of the first fraction and a 5 to the nth power in the numerator of the second fraction. And since they're being multiplied together, they're canceled out, which leaves me with the following. The limit as n goes to infinity of n plus 1 squared plus 1 over 5 times 1 over n squared plus 1, absolute value. I have two fractions now, so I'm going to multiply them together. And I get limit as n goes to infinity of following. One thing that I'm going to do for later is I note that I have a constant of 5 in the denominator. So that means I have a constant of 1/5. So I'm just moving the 1/5 up to the front and multiplying that by the n+1 squared plus 1 over n squared plus 1, absolute value. One-fifth is a constant with respect to n. So if I'm taking a limit of a constant multiple, I can move that constant up front. 1/5 is a positive number, so absolute value of 1/5 is just 1/5. So I can take the 1/5 up front, and I now have the limit as n goes to infinity, absolute value of n plus 1 squared plus 1 divided by n squared plus 1. Because the n's are coming from my index in my sum, or in my series, everything inside here is always going to be non-negative, and I can actually be stronger and say that they're all positive, which means that the absolute value is redundant, and I can rewrite as 1/5 times the limit as n goes to infinity of just, let's move that greater than or equal to 0 a little bit smaller. There we go. Of n plus 1 squared plus 1 divided by n squared plus 1. Now let's try to make this a little bit clearer to what that limit's going to be. I'm going to FOIL that binomial out. And once I do that, n plus 1 squared, that should give me n squared plus 2n plus 1. So I'm going to do that now. 1/5 times the limit as n goes to infinity. And all I changed was I FOILed out the n plus 1 squared. In my numerator, I have common terms of 1 plus 1. So I could combine them to give me n squared plus 2n plus 2. So now I'm taking the limit of a rational function, the highest power in the numerator equals the highest power in my denominator. So that means the limit will just be the ratio of the coefficients, which is just 1. So I get 1/5 times 1, which equals 1/5. And on a good day, 1/5 better be less than 1. Meaning that because of the ratio test, my series is convergent. And because I used the ratio test, I can be stronger and say that my series is absolutely convergent. So I'll write that as my conclusion. Therefore, by the ratio test, the series is absolutely convergent. Thanks for that comment, Anthony. When I first learned ratio tests, I thought it was cool too. So when I took Calc 2, I tried to use ratio tests in every single series I could think of, which made my professor kind of like stop it. But yeah. I'll pause for a minute if y'all are still writing back home, or if y'all have questions about this problem, post it on the chat or unmute your mic to let me know. I'll pause for a minute again so y'all can catch up on your home. All right. So my goal for today is to eventually to move on to power series, but before I do practice problems of power series and reviewing power series, there is one result that I do want to bring up for a reminder. Um, and based on what I've looked at old test threes for 1080, it seems that Dr. Burr really likes this problem, and that is remainder estimate for alternating series. Keep and recall that when I mean for alternating series, I mean I could rewrite the terms of my series as a -1 term raised to a power dependent on the index of my series times some positive term that I'll call b sub k. And what the remainder estimate for alternating series is saying is the following: is if an alternating series is convergent, then I can always estimate my remainder for that series with the positive term of my series, but not at the nth term, but evaluated at the next term over. Seems like kind of a weird thing to think of. I won't go through the full details as to why this works, so I'll kind of give a quick sketch. If that green line represents where my series converge, then what an alternating series is doing on my graph is it's bouncing back and forth above and below that line, and then I'm eventually going to level out where that line S is occurring. So what the remainder is saying is that my remainder is that distance from x to my nth partial sum. But the reason why I say it's less than b of n plus 1 is because it's less than the distance that I could have from any two other red dots that I could think of. So s of n plus 1 minus s of n. And if you expand and wrote this out, you're just left with one term remaining. So that's why we have that remainder estimate. Like I said, that's kind of a quick sketch of why I have the estimate. I won't go through the full details of it, but that's how we get it. And so I want to do an example where I get to use that. So let's say I have this alternating series, -1 to the kth power over 2k squared minus 1. And let's say I wanted to estimate with the fourth partial sum of that. And so a way that you could see this appearing as a question is what is the upper bound for the absolute error Fourier series? And to give you a recap, when I hear remainder, I'm thinking of absolute error. And so if you see this wording on the final, Dr. Bird means that she wants you to find an estimate for the remainder. And so let's go about and talk about how we could come up with a solution for our upper bound. So first, let's list out what I know. So I'm estimating with the fourth partial sum. Keep in mind that a remainder is defined as the difference between my convergent series and my nth partial sum. Meaning, if I'm estimating with SO4, that means I'm trying to find an upper bound for the fourth partial sum. If I estimated my series with the fourth partial sum. So in this problem, my subscript n is going to be 4. And here I also want to list down what my positive terms in my series is. It is the terms in my series if I neglect the -1 to the kth power. So 1 over 2k squared minus 1. So using our alternating series remainder theorem, if the absolute error of estimating my sum with the fourth partial sum is going to be less than or equal to the positive value term part of the term in my series evaluated at 5. Because I go to the next one over, I'm not evaluating at 4. So 1 over 2 times 5 squared minus 1. 5 squared is 25. 2 times 25 is 50. 50 minus 1 is 49. So what that tells me is the error that I have should be for that. When you're saying that, Anthony, are you referring to when I said BFK? Not in this scenario. When I'm referring to n, I'm referring to the subscript that's married with the partial sum. When I'm referring to BFK, and the reason why I chose the subscript k, I'm referring to the fifth here. The reason why is because let's scroll up, is to relate to the positive term with the remainder. I'm plugging in whatever value I have for n, and I'm adding 1 for it. So that becomes my k, or my specific k for that value. Whatever n was, plus 1. That comes like the nasty part of Unit 3. There's a lot of technicalities that we do have to take care of. So that's a really valid thing to ask, Anthony, and I appreciate that. Any other questions about this example? Again, I wanted to do one together with this because from what I've looked at from Dr. Bird's old test 3, she seems to really like this problem. because it appeared on all of her test 3s that I've seen. It's not necessarily a wink wink, it's just people are repetitive. People are creatures of habit. People are creatures of habit. If you like something, you're probably going to do that something again. All right. So now we're going to review power series and everything that occurs with it. So I forgot if I mentioned this in my videos for power series, but the reason why I made you suffer essentially to learn the series test is so we can now talk about power series and y'all know what we're talking about. So to recall what a power series is, a power series is a series in the general form I can write as such. People are not creative with power series because they honestly call it a power series because I have x being raised to the kth power times some constant in there. In a sense, that is a power series. Now this is a power series centered at 0. Because I don't have anything married with inside the x being subtracted 2. And I'm referring to a power series centered at A. Let's change that to P. And in general, my power series looks like similar to the previous series, but now it's x minus whatever I have for the center. And the reason why I call it the center is that value A is dependent on a lot of stuff. Where my radius is, where my interval is. Now, keep in mind that with series from before, we know very blatantly how to show convergence and how to show divergence. But the power series, because I have the value x in there, and I say that I can plug in whatever values that I want, I now have to be more careful about where do I converge. And that's why we have the interval of convergence. So interval convergence, to lay it down plain and simple, is the interval where a power series converges. That is essentially what a interval of convergence is. Now, a radius of convergence I think of radius of convergence as how far away am I allowed to go from x minus the center. So radius of convergence is just how far can I go from x minus a. So I'll write that down in like quotation marks. How far can I go from a distance between x minus a? And that's why our definition for a radius of convergence is that number r that appears when we're trying to set this guy up. And now another thing with this chapter is something called a Taylor polynomial. And I'll go ahead and say centered at A. The way you can think of a Taylor polynomial is if I have f of x and I want to approximate f evaluated at A. So let's say it's hard for me to specifically model my function. Actually, here's the better way to phrase it. Approximating f of x around the point A. Then the way that we do that is we define a Taylor polynomial as follows. First, my function evaluated at A, then its derivative at A times x minus A plus the second derivative of A over 2 factorial x minus A squared. And I keep going until I hit the nth derivative or wherever I want to approximate by. Should be n. And so if you want to see that in series notation, it will be the sum from k equals 0 to n, the kth derivative of function f at A over k factorial s minus A to the kth power. I agree, Anthony, and that's why we're doing kind of a review on this, because with power series and Taylor series, we're kind of going, here it is, go to town with it. I agree with you, Anthony. It is easy to forget some stuff. Just like in class, I forgot how to spell area. That was wonderful. You'll learn that comes when you learn more stuff. And so the power of a Taylor polynomial is it approximates my function where at the center I equal if I plug a in to use polynomial. If I take the derivative and then evaluate at a for the Taylor polynomial, I'll match up with f prime. So I'll write that down. Some cool properties of a Taylor polynomial. If I plug in a, I get back my function evaluated at a. If I take the first derivative, and if I say, let's plug in a, I say that I'm going to also match the first derivative of the function f evaluated at a. And I guess to keep on going, if I did the nth polynomial, taking a lot of derivatives, to get that I exactly equal f of n of a. And so that's the main reason why people care about a Taylor polynomial. Is a Taylor polynomial is a good way to approximate a function around a point A where it might be hard to figure out what the exact value is. And so with that, a Taylor series is the quickest way I can say it. It is a power series and a Taylor polynomial combined together. Or it's a power series where my arbitrary constant C of k that we had before, they're now exactly the coefficients that we saw from a Taylor polynomial. Another way that you could think of a Taylor polynomial is in the sum notation, we let the degree or the highest power of my Taylor polynomial blow up to infinity. And that's a Taylor series. And the cool thing that we've showed is for the majority of functions in this class, we can actually show that a function is equal to its Taylor polynomial centered at a point. And we typically talk about Maclaurin series because it's a lot easier to talk about Maclaurin series. And when I say Maclaurin series, it is the laziest definition I could think of. It is a Taylor series where the center is 0. And that's why we typically talk about Maclaurin series with a function. And why we typically give y'all yets to represent a function in the class based off of a Maclaurin series, because it's a lot more smoother to work with that. Alrighty. And so with that crash course, let's dive into problems. It's just like with series, power series and Taylor series, the best way to learn them is to get your hands dirty with problems. And so here's the first practice problem from here. And this is going to use a property of power series that is going to be abused essentially throughout this whole semester. So I'll go ahead and give you one Maclaurin series, and that's 1 over 1 minus f. And yes, this is Maclaurin series. I'm not going to tell you to derive it. I'll just give this to you. And I'll tell you that the series converges when it's strictly less than 1. So with that fact, use that fact to identify a function represented by the power series the sum going from k equals 0 to infinity, x to the k plus 1 power raised to due to the kth power. So for this problem, the only information that we have is here's the Maclaurin series for the function 1 over 1 minus x. Using that fact, let's see if y'all can find another function to represent the following power series that I have boxed in. I'll give y'all a few minutes to work on that. If y'all have questions, please let me know. I'll be happy to answer them. And I'll give y'all about 5 to 6 minutes to work on it before I go to a solution. All right. I'll keep working on this. I'll give y'all about 2 to 3 more minutes before I go to solution. Like I said, if y'all have questions, please let me know. Alrighty. Let's go over the solution. So my first thought is, how can I try to transform it into something like s to the k power, so I can use the fact that it equals 1 over 1 minus x. Now, with this, always think of that x as an input, meaning whatever is in that slot of x is going to be in that slot within my power series. And so what I need to do is transform my power series into that scenario. So let's do that. I have x to the k plus 1 over 2k. The first thing that I'm noticing that is very beneficial is I have k's occurring within the exponent. And that's nice because I can then use my property of exponents that says if the numerator and denominator are being raised by the same power, it's the exact same thing as me saying a divided by b raised to the power k. However, I still have that plus 1 in the numerator, in the exponent of the numerator. So I need to split that guy up to give me x to the k power times x times 2 to the k. Well, so far so good. But now I got to figure out what I'm going to do with that x. Here's the cool part about power series, in my opinion. That series tells me that anything that has k defined in it, I must stay within my series. Yes, x does not have k with it. So as far as I'm concerned, yes, x is treated as a constant. With respect to my series. And the reason why that's beneficial is if I have a constant in my series, I can take it outside of my series and then just take the sum of what's left behind, meaning that x is now outside of my sum, and I now have x to the k power divided by 2 to the k power. Now I have what I wanted with that property. I can now rewrite s to the k power and 2 to the k power as x over 2 to the k power. So I now have x times the sum from k equals 1 to infinity of x over 2 k. And now I have something that is very similar to what we had originally. And like I mentioned, whatever is with that x, I'm treating that as an input. So what that means, x over 2 I treat as my input. And so now I get to use that fact of the power series representation of 1 over 1 plus x to rewrite this as 1 over 1 minus, but I'm not going to write x because I have x divided by 2 raised to the kth power. So I'm going to write 1 minus s divided by 2 in the denominator. And then multiplying the s with everything, I simplify to get s divided by 1 minus s over 2. Give me my final sum for that series. I'll pause if y'all start writing down. If y'all have questions, please ask me and I'll be happy to answer. And so what this sample illustrates is a property of power series that y'all used on the take-home quiz, and something that's very useful throughout when you're dealing with power series. And so because of that, I'm going to write those as facts for us to work with. So here's fact number 1. If I have any x raised by a power of k, actually let's change that to an m. I have c of k, x of k. Then the first property that I can do is that x to the m can go inside my power series, and I can do what you would want, which is add the exponents together to combine them. So that will be x to the k plus m power. And I use that property on this line in reverse to justify why I can take the x outside of the series. The second property that I used to justify why I can replace x over 2 when I did this step is the following. If I know that I can represent the function f as a power series, and I have h to be rewritten as some constant that I don't know about times x to the m, then the power series representation of f composite with h of x is equal to my power series, but where I had an x originally, I'm replacing with that h of x. And in this case, from our previous example, h was x over 2. Get positive inside. So those were the properties that I used. Let's talk about some more properties of power series before we go of any more Taylor series type problems. And that is integrating and differentiating power series. So let's talk about how we do that. And this is going to hold about the Maclaurin series as well. And so what this is saying, if I know for a fact that I can represent a function as a power series then what I could do for taking the derivative and taking the integral is I could do it term by term. And so let's talk about what that means. If I'm taking derivative of f of x, then because I can represent f as a power series, I'm multiplying by that power series representation. What take a derivative of power series tells us is I can move taking that derivative inside and take derivatives term by term. So what YesStuff is saying is that derivatives of power series is taking the derivative term by term. And those are some hyphens to combine those together. And the reason why it's nice for term by term differentiation, this is just a constant times x to the k. Well, derivative of x to some power, that's just power rule. And we know how to take that way back in the day when we took 1060. So if I took the derivative, I'm going to have c of k, well, that's just a constant. Constant multiple tells me I can take the constant out of the derivative and then take derivative of what's left behind. And my power rule, it'll be k times x to the k minus 1. Now the tricky thing about derivatives that gets a lot of people with notation part is I actually lose one term with that derivative before that. So my series will actually begin at 1 and not begin at 0. So that's one thing to note about that. And now let's talk about taking the integral of that. Taking the integral is very similar to taking the derivative term by term. Is that I'm going to move that integral inside my power series. So integral of the sum equals 0 to infinity of c of k x of k dx tells me that I can integrate term by term, which is super nice for me to do because I'm taking a derivative just term by term for that. And so let's see what that looks like. So because it's an indefinite integral, you're going to have a constant plus c. I'm going to move that plus c up front to not get it confused with it being inside the series. I want to make sure it's outside of the series. Plus the sum, k equals 0 to infinity, that constant, x to the kth power. So whatever was in my exponent, because I'm doing my antiderivative rule for the power rule, I add 1 to the old exponent, and then I divide by the brand new exponent. And that's how we take integrals and derivatives in a nutshell. And so with that, let's try to do one example where we're going to have to use some of that fact in there. Here's going to be the example I give y'all to kind of help combine some stuff. Find a power series representation of the following function. F equals x divided by 2 minus x cubed. Or one way you could rewrite s cubed multiplied by 1 minus 1 divided by 2 minus x cubed. And I rewrote f of x like that on purpose to kind of help y'all out. But for it, so I want to give y'all a hint too, to kind of figure out how to tackle this problem. So here's my hint. How does the 1 over 2 minus x cubed relate to 1 over 2 minus x? I say that there's a relationship between those two. I want to see if y'all got it. If y'all have questions, let me know. And I'll give y'all about 8 to 10 minutes to work on it before I go over a solution. So give me a status report on this problem, guys. How are y'all doing on it? Keep working through it, but I just want to know how y'all are doing on this problem. Answer your question, Margaret. Yep. That should be the relationship that we should see. Is that I relate this to the second derivative in some way, shape, or form. I noticed that the time is 5:22, so for the sake of time, I want to go ahead and go over the solution for that. As Margaret pointed out, the relationship between 1 divided by 2 minus x and 1 divided by 2 s minus 3 is that it's related to the second derivative. So let's check that. The derivative of 1 over 2 minus x, that's the derivative of 2 minus x to the negative first power equals negative 2 minus x negative 2 by chain rule. But then I have a negative 1 to complete the chain rule. So I have 2 minus x negative 2, or 1 divided by 2 minus x squared. Not quite what I got, but let's take the second derivative of that guy now, of 1 over 2 minus x. Second derivative is the derivative of first derivative. And by chain rule, I get the following. Negative 2, 2 minus x to negative cubed times a negative 1. So I have 2 over 2 at 2 minus x, not 2x cubed. And that's very close to what I have for 1 over 2 minus x cubed, which implies if I had a constant of 1/2 being multiplied up front, when I did this, I get back to the 1 over 2 minus x cubed that appeared within the original function that we're talking about. So that means the relationship that I have between 1 over 2 minus x to the cubed power and 1 divided by 2 minus x is 1/2 times the second derivative of 1 over 2 minus x gives me the 1 over 2 minus x, all of that cubed. So let's first talk about the power series of 1 over 2 minus x. Because I'm going to use that take a derivative term by term to help me in that. So let's get that real quick. And so what I have is the following. It looks very similar to the 1 over 1 minus x, but I can't apply that formula yet because of that 2. And so what I have to do is I'm going to have to factor out a 2 in my denominator to give me a 1 minus something. In this case, 2 times 1 minus x over 2. Or 1/2 times 1 over 1 minus x over 2. We saw that back in our original, in one of our previous problems. So that gives me the power series sum from k goes from 0 to infinity of x divided by 2 to the kth power. And I'm writing this down just to make a note that for that series to converge, the absolute value of the term within that kth power has to be strictly less than 1 for that. Rewriting, I have x to the k over 2 to the kth power. And I can move that 1/2 up front inside the series and get in my denominator 2 to the k plus 1. So that means my series that represents 1 over 2 minus x is x to the k divided by 2 raised to the k plus 1 power. So now let's talk about how we can get the power series for a second derivative, which we got to be 2 divided by 2 minus x cubed. So let's check that. So we know that 2 2 minus x cubed relates to 1 over 2 minus x as the second derivative appearing for that guy. Okay. I already know this power series. As the sum from k goes from 0 to infinity of x to the kth power, let's stick in pink, x to the kth power over 2 to the k plus 1. And just like before, we're going to take derivative term by term. So I'm first going to take the first derivative inside that series and have the derivative with respect to x of x to the k over 2k plus 1. And what I get from that is inside the parentheses, I now get the sum. Because I took a derivative, I lose one term, so now it equals 1 to infinity of k over 2k plus 1 x to the k minus 1. Keep in mind that derivative of x to the k by power rule is k times x to the k minus 1. So that's how I got that. Because I still have to take another derivative, I'm going to move the derivative again inside what I currently have. K over 2k plus 1 are constants, so I'm only taking derivative of x to the k minus 1, which is another application of the power rule, which now gives me a sum k starting at 2, not at 1 anymore, of k times k minus 1 over 2 to the k plus 1 x to the k minus 2 power. And what I'm about to do is probably going to seem like magic, but here's kind of my thought process. As nasty as is, the fact that your sum's already starting at 2. And so what I'm doing is something called change to sum index. And here's my thought process of it. I want my sum to start at 0. I don't want it to start at 2. So currently I have that my series begins at 2. I want it to begin at 0. And for me to begin at 0, I'll have to move backwards 2 units in order to get that. And so because of that, I define a brand new value m to equal k minus 2 to accomplish the fact that I want to start my series at 0 and not start my series at 2. And let's check how that would affect and change our series. So because I'm doing a change of my sum index, because m equals k minus 2, and I started at, and k equal 2 at the very beginning, that means m's going to start at 0, which is what I want. And everywhere that I see a k originally, I'm now going to change in accordance to m. And so let's do that. And let's do that on the side. So if m is k minus 2, then that means I know that m plus 2 equals k based off that equation. So that means in my sum, if I just have a k isolated by itself, I can replace with m plus 2. So I do that again here. I have a k here, so that is m plus 2. And then I have a minus 1 appearing. For that. Oh, hold on. Not quite for that. My apologies. Yeah, you're good. Okay. And now for the k minus 1, for that guy, to rewrite k minus 1, yeah, that's it. No, it's m plus 1. Okay. I overdot. Sorry, guys. So m plus 2 minus 1. Got a little too greedy. Just want to make sure. Everywhere I saw a k, I am replaced with m plus 2. Plus 1, that's m plus 2 minus 2. That's going to change to a plus 1. The exponent with 2 is going to change to m plus 3. The exponent with x is just going to change to m. And so I now have a sum that begins at 0, m plus 2, m plus 1, 2 raised to the m plus 3, x to the m power. And so that's cool. I have a power series of the second derivative. Now let's go back and form a power series for f of x, which was x cubed over 2 minus x cubed, or x cubed over multiplied by 1 minus 2 minus x cubed. I can't substitute the power series that we found back in yet because I don't have a 2 in the numerator, but I can multiply by 1 to give me a 2 in the denominator and numerator. Now what I have is I now know this power series of 2 over 2x minus 3. So I can now substitute that in as follows. And I say now we get to win and profit from our hard work. I have an x cubed over 2 outside. I can move that inside my series to give me my final result. M equals 0. 2 raised 2. This is I'm multiplying by 2 in that denominator outside the sum. When I move it inside the sum, and combine like terms, I'll have m plus 4 plus 1. I move the x cubed inside the power series. So now I have the following as my power series to represent f of x that we have above, which took us a very long time to get, but we could do it. Does anyone have any questions about this example in any way, shape, or form? Or any comments?
That was fun.
Yeah, it was a lot more work than we're used to doing. It is so we're used to just doing the first derivative. We could also do it for the second derivative. It's just going to take a very long time. Since this afternoon meeting, do y'all have any questions for me in general about the final or about take-home quiz 12 or anything of that nature? All right, go ahead and shoot, Unique. What problem are you referring to, Unique, on the take-home quiz? One A. Got you. So when you're forming a new interval for that, and let's scroll down and do take-home quiz 1A. So to summarize Unique's question, in 1, we have the following parametric equation. And our parameter is bounded by 25. When we're trying to form a brand new interval for yets, back we would for x and y. Here's kind of my idea for that. To form an interval in Cartesian coordinates. What I'm referring to, Unique, is based off of our parameter, how's that in Cartesian coordinates going to affect our independent variable? And so because of that, my interval, if I call this for my parameters alpha and beta, my new interval for the problem is going to be determined by my parametric equation married with x evaluated at alpha, and I'll use f to correspond with the lecture notes. That's f of t and that's g of t. And also my parametric equation plugged in at what beta is. That's what I'm referring to when I say find a new interval is, if we're going back to Cartesian coordinates, what interval would my independent variable be, or what interval is x lying in? And I'll just be plugging it in. Yeah, you're exactly right. And that's essentially how we find a brand new interval for that. No, it's okay. With the parametric and polar stuff, like I told one of your classmates a couple days ago, it's very easy to overthink about it, about parametric and polar. But the rules, some of the things that we could do for Cartesian, we could also do for parametric and polar. So if you ever thought it, I understand why. Any other questions?
I just want to say thank you, Scooter. You've been really good this semester.
Oh, you're welcome.
Thank you, Scooter.
You're welcome. I actually talked to Peter today, and he is very happy that he's essentially made a whole class call me Scooter.
Well, we call him Cute Peter, so
Yeah,
he's more happy about that.
Bounces out.
Yeah. Oh yeah, that definitely evens it out. Doesn't care. All right.
When you get your PhD, we can call you Doc Scoot.
Ooh.
That's so true.
Gosh. Yeah, I will definitely ask Clemson University to print it on a piece of paper that I get at the end that says I have a PhD.
Peak middle
Legally change your
performance.
name.
Scott. Oh, no middle name.
Alrighty, well, you have a good day.
All right, you too.
All right, yeah, have a good day.
All righty.
Just look on the final.
We will. Thank you, Unique. If anyone else does have questions, I'll end the meeting. It's been a pleasure being your instructor. Expect to hear some announcements from me, and stay strong. We got this. After Monday, 1080 has now been over. All right. See y'all.